All right, happy Wednesday, everyone. Our warm-up for the day. Take this scenario, decide how you are going to transform this scenario into a graph. Remember that graphs are those sets of vertices and then edges, the links between the vertices. Technically, a tree is a type of graph, but the difference with the graph is that you can have as many pointers in any direction from any node to any other node. So go ahead, chat with the folks around you, remind yourself what all these words mean, and we'll come back together in 3 minutes. All right, we have a ton of stuff to get through today. Also, because I want to give us plenty of time to talk about the midterm and answer any and all questions you have. So let's pop over and take a look at how the Slido is shaping up. This is the one. Okay. We've got 67 responses. Ooh, 69. Okay. So how would you represent the follows connection in our given graph? Let's see, we're getting a few more votes, a few more. Remember that vertices, that's the word we're using for nodes now. Edges, that's the connections between vertices. Direction means whether or not there's an arrow at one end of your edges. And I like to think of those as one-way streets in that direction. So if they're not directed, then the connection is bidirectional. If they are directed edges, then whatever arrow, whichever way it's pointing, that's the only way you can travel. And weighted edges are when we apply a value that sits on a top of an edge, because we can now store information in our relationships. A classic example might be like distances. Maybe that's your weight. Or traffic heaviness or something like that. Okay, now that we're at 90 votes, I'm going to hit show results. Let's see. Aha! Directed edges, 94%. Does anybody want to raise their hand and tell me what they would sort of use as a design for this graph? What are your vertices? What are your edges in our scenario? Because I do agree with the consensus here about directed answers. What do we discuss as our organization? Yeah, way in the back. What do you got? Yep. Vertices are profiles. And the edges are the relationships. So in this case, if someone, let's say profile A followed profile B, what would the edges between those two look like? Pointing to B, yes, meaning like A follows B, but following is sort of a one-way direction, right? If only all of those blue check marks followed us back automatically. Different from, say, what if you were friends and that's a bi-directional relationship? How would you represent? Yes, you would need two arrows, one pointing in sort of both directions to represent a bi-directional relationship. I like it. So here is the answers that I got. So profiles, directed, and right now unweighted. Just the existence of those sort of connections between the vertices represents a like clicking of a follow or clicking of a friend. You could maybe imagine a scenario where you could try to map influence, and maybe the weight of those connections is their follower count, meaning there's more weight when you get followed by somebody that has a lot of followers, kind of thing. That is how actually a lot of the influence mapping is calculated. Any questions on how we came up with this sort of design? You will be asked to do this type of design on your exercise. There is a strong possibility you will be asked to do this type of design on the final exam. But make it more complicated. Any other questions, thoughts? Okay. Cool. Okay. There's a second one in here. In the interest of time, I don't have a ton of time to go over it, but I thought this one was cute. You're at a music festival, and you're trying to map that as a graph. And so you've got artists and their sort of singular performances, and you're trying to figure out what sequence of artists you will see in what order. And so the previous one was about profiles and relationships. This is almost about states. Like, how do you travel from one state, meaning seeing no musicians, to a final state, meaning seeing the most musicians you can, kind of thing. And so in this context, the vertices would be the artists, and the edges would be possible choices. And so sort of building out this set of possible choices when you travel the graph, then you can kind of get some of the permutations for what your options might be. So another way to think about graphs. Okay. Great, let's get to the part that I'm sure we all want to talk about. If you haven't checked your email, we officially did release the midterm grades about 30 minutes ago or so. There are some logistics to go over. So first of all, here is the distribution of the scores. Congratulations, a beautifully normal distribution. The median is 51.5, but remember, there is a resubmission coming. So I will admit, our goal was to make these questions complicated enough that it's worth you doing them twice. There's no reason for me to give you a simple exam and then you just spit back out to me what you did wrong to resubmit it. So now that you have your grade, remember that the way the resubmission works is that there is an online submission. You do not have to resubmit every individual question. If you like your score on the original one, you don't want to resubmit it, you just write skip. This is a no-risk resubmission. We will take the greater of your two answers regardless for your secondary score. So you cannot end up with a lower score on the resubmission. Then at the end, we will average your two scores together, and that will be your final exam score. So this is the score that you got timed without a computer, without anything electronic, without being able to speak to people. Now you have a week to do what is essentially an hour's worth of work, and I do expect you to speak to one another, to discuss the answers, to find things on the internet, to reformulate and give us the best possible answer. I am expecting the scores on the resubmissions to be pretty high. So, as you can imagine then, if our average was around 50 on the first round, and then our average is pretty close to 100 on the second round, we're going to end up with an overall median probably in the 70 to 80 range, which is generally where I like my exam averages to roll out. So this is a little bit of an experiment, but so far things are looking pretty good for your overall performance in the class, everyone. We are going to take your resubmissions and grade them as if they are an independent exam. After you receive your grades for the resubmission, we will open up regrade requests for both of the exams. So, for example, if you're going over your current version and how it's graded, and you have any questions, like you're not sure why it was graded the way that it was graded, or maybe you even sort of are unsure if you got the grade you thought you deserved, you are welcome to make an ed post. We are only answering questions about the midterm on ed. That's mostly just because it's way easier for us to keep consistent. As you can imagine, we want to make sure that you get an answer from the TA that actually graded that particular question. And we want everybody to get the same amount of information. So if you ask a question about the midterm, specifically your grading during office hours, the TAs will say, sorry, I can't answer those. Please put a post on ed, make it a private post. That's just for consistency and fairness to make sure you get the best answer possible. Let's see, what else did I put on here? I think I answered all these things. Yes, and then we will open up regrade requests. So if you do find an actual error, we will regrade and give you the higher score on even the first one if you catch something like that. But you'll probably find it in your revisions along the way. Okay. Questions? Questions? Really? I feel like there would be a lot of questions right now. This is such a weird thing we asked you to do. Yes?
What's the percentage of this in our final grade?
15%. And we will do this exact same thing for the final. They are worth the same percentage. The final will be like it can't really not be cumulative in this class. We're sort of learning things on top of each other, but the final exam will be focused on topics starting from week 5 onward. So the midterm was weeks 1 through 4. The final exam is going to be in week 9, so it will be on weeks 4 through 8. I'm going to pop open the Slido. Maybe there's some spicy questions we didn't want to ask in person. Yeah? There is resubmissions for the final. We're going to do this exact same process. That's why we're giving the final in week 9. Right? It's week 9? Yeah, thank you. So you'll do this exact same thing all over again for the final. Let's see what's on Slido. Cool. Oh my gosh. Big Bud Press, y'all. Big Bud Press. Incredible company. Gender neutral company. Adore it. Thank you. I'm not gonna lie, I left the house this morning and my partner was like, is that teaching appropriate? And I was like, it is now. All right. Ooh, yeah, okay. I did post a hackathon yesterday. Actually, that hackathon is being run by a former 373 student. It's at Bellevue College, and it is specifically for... Ooh. I like this hustle. Oh, if you say so. Cool. All right. Let's see. Yes, I will say to answer this question, this is actually terrifyingly exactly where we wanted the distribution. We wanted a normal distribution. There's a nice range. There's a decent standard deviation. And we knew if the first round was around a 50% average, that the final result was going to be around a 75% average. And I generally like an average between 75 and 80. Cool. Oh, now we're not feeling so confident. Those questions disappeared, huh? Or did you all resolve them? No. Oh, the submitter resolved it. Okay. But yeah, do take a look at that hackathon. It is specifically targeted to marginalized genders, and it is at Bellevue College on May 13th, which is really fun. I guess the TAs. Those TAs, how reasonable. All right. Okay, go on. Incredible. Any other questions that came up for anyone? No. All right. Then let's dive back in, y'all. Okay. So on Monday, we met this entity called the graph. We picked up a bunch of terminology, and we ended with some conversations about how to actually implement it, the adjacency matrix and the adjacency list. Now that we have this foundation, this is a model, right? It's a model for a scenario. And I've been kind of asking you to model things without actually showing you what we can do with the models. But pretty much for the rest of this unit, I am going to be showing you some really cool algorithms that you can apply once you translate your scenario into graph form. It's the source of a lot of interview questions. It's frankly the source of a lot of your favorite software. So let's get into it. Okay, let's say we have a graph that looks like this, and we want to just determine if some vertex S source is in some way connected via however many vertices and edges to some other vertex T terminal. So this is the S to T connectivity problem. And remember, graphs don't all have to be connected. You could just have a vertice sort of floating about in space. So we, by default, don't necessarily know if we can get from one vertex to another. The way that we will determine this is we are going to actually write code that crawls through the graph. So the sort of way to think about this is we can use recursion. We can ask, hey, if a neighbor of S is connected to T, that means like by transitive property, eventually we can find a way through. So we're going to do this thing, we sort of check neighbors of neighbors of neighbors of neighbors until we eventually find if we can get to T by crawling from neighbor to neighbor through the graph. So here is our first bit of code. We take in the two vertices, S and T. If they're the same, great. We are connected. Otherwise, for all of the neighbors of S, we will loop over them and ask, are they connected to T? However, right now, this doesn't do a very good job because it's going to just check my immediate neighbors. It's going to be like, hey, is ST? No. Is the neighbor of S, which is this one right here, is that 7? No. And then it'll loop back around and it'll just keep checking 0 to 7. So we get sort of stuck in this infinite loop within the neighbors here. So whenever we are traveling, whenever we're crawling through a graph, we need to include another structure that will keep track of where we've been. So this is also welcome to graphs are so often code that involves just a collection of a lot of data structures. That's how we manage to do all these things. Also part of why they're such popular interview questions. So we are going to make a set called visited, and every time we look at a given vertex, if it is not the terminal vertex, we're going to put it into this set of visited, and then when we're asking ourselves, where do we explore next, we will check, hey, have we not visited that thing yet? If so, then go ahead, do our little recursion. Otherwise, skip it so we won't get in that infinite recursion loop. So the idea is that we start at S, we look at the set of neighbors, and then we look at the set of neighbors. So 1's neighbors are 4 and 2. We look at 4's neighbors, 3 and 5, 2's neighbors, 5, so on and so forth. And we crawl through the graph, making sure that we keep track of where we have been before so that we are always making forward momentum progress in our code here. This outline is the foundation of almost all of the algorithms we are going to be building. I'm going to show you an iterative example of this as well, but this sort of idea of start at a vertex, keep a set of where you've been, look at your neighbors, repeat until you get to where you're going, that's the foundation of almost all of these algorithms. The difference might be how you explore the neighbors or what questions you're asking yourself as you go through and crawl. But this is kind of the equivalent of like a for loop that just runs over the array. Like if that's how you just sort of move over the array, or like a public-private recursive pair that lets you get from the top of the tree down to the bottom of the tree. This is sort of your graph traversal code. Any questions on it so far before I make it more complicated? I came out really Canadian. Okay, so what this is called, this algorithm here, is called depth first search. You will often hear it referred to as DFS. And the reason it is called depth first search is because we sort of do this like direct plunge into neighbors where we would start at source, and like source has two neighbors, 4 and 2, but we're going to explore, like if 4 is the first neighbor we're going to look at, then we're going to look at 4's neighbors before we ever come back around and look at the other neighbors of 1. So it's kind of like we follow a singular chain of neighbors before we come back around to finish all of the original neighbors of 1. So this is why we sort of call it depth first search. I think of it as like, you know, you're sort of digging through a tunnel all the way to the end before you come back around and look at the other pathways through. The thing about this too, when you're running DFS, is there's actually a lot of different orderings that could be relevant here. It all depends on which neighbor you start to explore first and which neighbors of neighbor you explore first. So this is not a deterministic ordering unless we give you some type of thing that's like visit the neighbors in sorted order or something like that. But usually it doesn't have that kind of requirement on it unless you yourself add it because you need to adapt this algorithm in some particular way. So this is depth first search. This is I explore all the neighbors of my neighbor before I come back around and look at my second neighbor. So you can see, oh, thank you, Pass Casey. It sort of does this like exploration down a singular path, and then it finally gets to the end, and then it comes back around, and it sort of cleans up the nodes it didn't see. So whenever you sort of look at these visualizations, and if you're curious, all the graph algorithms we are going to be learning about have infinite YouTube visualizations, and you can sort of go watch them, and you'll see depth first search. It sort of draws these lines through the entire graph. Like you get this one consistent path, and then it'll come back and it kind of cleans up the remaining bits. Sort of a nature of DFS. Great. So remember that technically, by our definition, trees are all sort of like specialized versions of graphs. I think of tree is to graph as square is to rectangle. Do they still do those on the SAT? Is that a thing still? No, I'm old. Never mind. But I think depth first search is really clearly visible if you run it on a tree. Oh, thanks. I even timed that one. Wow, there you go. See, we're going from the top all the way down to the depth before we come back up. You're like, Casey, we get it. Why are you telling us about this ordering so much? Because welcome to depth first search's twin, maybe, at least sibling, breadth first search. Breadth first search is the same idea. It's just going to travel all of the connected vertices of the graph. It's testing connectivity, but instead of visiting the neighbors, I process all the neighbors immediately connected to the source first. And then I process all of the secondary neighbors then. And so you end up with this sort of like rungs kind of thing. Sorry, I over-animated myself. So say it starts there, and then I kind of do the ones most close to me, and then I do the next ring out, and then the next ring out, and then the next ring out. So it visualizes, and I like to sort of think of it as like rungs or like orders of distance from the source, sort of waves all at once going out. Question?
So if you're starting at 1, is there a particular order between which it processes first between 2 and 4?
Great question. So is there an order between 2 and 4? Right now, by definition of the algorithm, no. If I were to ask you to, say, perform this algorithm on your exercise, and I need a deterministic order so I can grade it, I will give you something that's like visit the neighbors in sorted order. That's usually the easiest way to do it. But that's just something I'm doing to sort of give you a specific way to approach this. It also leaves it open for interpretation depending on your scenario. So there's still even flexibility in which of the immediate neighbors you process and in what order you process them. Layer by layer. Oh yeah, there. That's the animation I really like. So you can kind of see it sort of explores these. Okay, so that's our goal. How do we write this code? So the code that I showed you before for DFS was recursive code. Because this does apply recursively, but that worked really well for depth first search because when you make a recursive call, it like interrupts the work you're doing to start a new line of work. So it's really easy to do that sort of depth kind of like purge into the graph or whatever you want to call it. Now, we don't necessarily want to interrupt ourselves to keep going neighbors of neighbors of neighbors. I kind of want to allow myself to like fully explore the layer around me before I continue. So we are going to write this instead of recursively, we are going to loop over all of my neighbors. So instead of recursion, we are going to use iteration, but this means that we need a way to sort of queue up the neighbors so I can like loop over all of my neighbors and know that I've processed all of them before I move to the next layer. So here is the BFS implementation. Right now it is taking in this object called graph of type graph. You'll see me do this in the slides. I don't actually expect you to implement it this way. It just makes it a little easier for me to sort of like fit everything on a slide. But you can kind of think of that as like, it's like a pseudocode conceptual graph right now. So, yeah, great, thanks, pass Casey. Okay, so what we are going to do now is we are going to add another structure. We already added one to tell us where we've been. Now this is going to tell us where we have yet to go. So you could call it perimeter, you could call it like to visit, you could call it neighbors left to go, something like that. And then we have our set from before, visited, like where I've already processed, so don't reprocess them. So what we do is we initially add the start vertex into both. That's like the only time we kind of do that all at once. So it's like when I'm standing on S, I need to process it, but I've also kind of visited it. And that's what's going to kick off our while loop that is going to be based on the things yet to visit. So I add the first source target in the things yet to visit. Then I get all of the vertices that it is connected to. This loop just goes over all of the edges, and you can see it just pulls all of the neighbors. And then it goes neighbor by neighbor, and it asks, have I visited you before? Skip it. Otherwise, add it to the perimeter. And then loop around. Cool. Great. So here's how it works. We add 1 to the queue. We pull out 1. We're now here on this line of code where from is now equal to start. But then I'm going to loop over and I'm going to add 2 and 4 into the queue. Great. I pull 2 out. 2 is now my from. And I loop over and 2 is connected to 5. So I add that into the queue. But see how that lets me come back and finish processing 4 that I added earlier in. So then I do that. So now I add in 4's neighbor, which is 3. And then I come back around and I process 5. And 5's neighbor is 6 and 8. And then I process 3. There were no new neighbors to 3 to add. And then I process 6. And it has 2 neighbors, 9 and 7. And then I process all of those and I've gone through everything. Any questions on that algorithm? I believe that's one of your exercise problems, is to sort of perform these types of things. Great. Yes. So there you go. That's sort of the orders in which we visit things. And the queue kind of works perfectly, right? Because a queue is all about first in, first out. So as we meet new nodes to visit, as we meet new vertices, we're like, get in the back of the line, there's someone ahead of you, and I've got to deal with it. Their business comes first, which is exactly the functionality we're looking for. So thanks, queue. What if we wanted to take this code, this BFS code that is iterative, not recursive, and transform it into DFS? I could tell you right now, I can make a single line change to this code that will transform this from BFS into DFS, and it is all just about how I store the order of the vertices I have yet to visit. That determines the order in which I visit them. Can anyone guess? Anyone see where I'm going with this? Yeah. Use a stack. Oh, so clever. Ha-ha. There we go. Because a stack is that opposite type of behavior, right? As we meet a new node to visit, we push it onto the top of the stack, and anything that's been waiting around to visit gets pushed further down. So because of the stack, we will get that same sort of neighbors of neighbors of neighbors plunge into the graph type of behavior. Any questions? Cool. Great. We really appreciate the venom. All right. Yes. Me too. Oh, yeah. And there's this one change there, but you can read these things. Okay. So that code there and the logic behind it, like I said, truly is the foundation of all of the algorithms we're going to write. Just a little aside here. I show you all of them so you have all of those things in your toolbox. But actually, if you run the recursive DFS on a graph of any meaningful size, you're going to get a Stack Overflow error. Also, this is a moment that I should tell you, I've never written a line of professional recursive code because recursive code is almost always really inefficient compared to iterative code, though it might look elegantly beautiful. So those of you that hate recursion feel vindicated in this moment. Yes, questions? Yes. Oh, thank you. Yes. Once upon a time, I had a lot more pop culture references in this, but I'm not going to lie, they all got outdated. Listen, it's... Okay, friends in the office, I will say I first made these the graph slides right before the Game of Thrones, season 5 reveal, and I thought I was so clever, but it's really outdated now. Surprise. Oh, I'm going to spoil it. It's old, right? I was like, surprise, Jon Snow's related to Daenerys. Ha ha. That was my whole pitch. Okay, anyway. Yeah, great. Thanks, Pass KC. Okay, cool. Okay, so now that we have this code, we can write this code to test whether two nodes are connected via some intermediary path. Because both BFS and DFS, if let just run to their conclusion, will just process all of the nodes that are connected to one another in the graph. So this is a good way to determine, hey, is my node in some way connected to some other node? It's also, like I said, the foundation for maybe you need to count how many nodes are connected, or maybe you need to count the overall weights of what's connected, or something like that. But you can also imagine a scenario where you run these algorithms and you don't let them run to their completion. So maybe you want to find just one path. So you run DFS, and as soon as you find target, you bail out. You don't need to keep going. Or maybe you want to run 6 degrees of Kevin Bacon, and you do sort of 6 layers out from BFS, and then you're done. You don't need to finish BFS. So again, you can take these algorithms and tweak them to answer the question that you need to answer. That's pretty much all this slide is talking about. Okay. Cool. Any final questions on traversals? Okay. Yes? A great question. You're right, I didn't put the runtime on any of these. So right now, all of these traversals are going to have what we would call graph linear runtime, which you would write O of V plus E, because it's going to touch every vertex and it's going to explore every edge. So that's graph linear. And it's kind of just do them in this one like linear process crawl. So it's sort of like it touches every vertex once, it touches every edge once, so on and so forth. Cool. Good question. Thank you. Okay. Okay, I'm sorry. This is a really delightful algorithm that is super useful, but it's like never fits really well in any other places. So it's a little bit of a kind of like detour, and we're going to come back around to like the BFS DFS code. But hold with me for a hot second. Okay. Topological sort. Topological sort of a directed acyclic graph provides an ordering of the nodes where every edge in the graph, the origin appears before the destination. It is a way to take this sort of like two-dimensional like map of graph sort of land and give me a linear ordering where every origin comes earlier in the ordering than a destination. This is literally the way that your compiler determines the order in which to compile your pieces of code. Because in your code, you know, at the very top when you've got your import statements and all that stuff, the computer sees those and it's like, oh, before I run this code, I better have this code available to me. And so it actually turns your code into a graph and runs a topological sort to determine the order in which to compile all of your pieces of code so that it has a compiled version of something you use later. It also applies to, great, cool. There you go. There's some sort of visuals. So if we have A pointing to B and C, but B points to C, a topological sort could be A then B then C with the original references. That's sort of where we're headed in this direction. Now the thing is that this will only work. One, you must have directed edges. If you remember in other traversals, what we were looking at before, those were undirected edges, just the connection needed. This one requires direction. It also has to be acyclic, meaning there can't be a cycle in your graph. If there's a perfect cycle, then there isn't really an ordering, and when you run this algorithm, you're going to get stuck in an infinite loop. So we are specifically looking for what is called a directed acyclic graph, often abbreviated as a DAG. Let's look at how this works. Okay, so here is a directed acyclic graph. The way that we do topological sort is we count up first what are the in-degrees of each vertex. So as you can imagine, something that has a high in-degree means that it has a lot of upstream dependencies. It's got to come later in our ordering. But something that has 0 in-degrees, then nothing has to come before it. So we look at this and we ask ourselves, which node has 0 incoming edges? And right now it's A. So what we're going to do is we're going to put A at the beginning of our ordering, and then we sort of like erase A and readjust those in-degrees, and we see, oh, now C has 0 in-degrees. Well, we'll put that next in the ordering, and then we'll sort of erase C, and then we've got 3 that now all have an in-degree of 0, and what that means is that topological sort actually could have multiple orderings. But at this point, the order of B than D, wow, I got real fancy with these animations. Okay, than E, the B, D, E, that's somewhat arbitrary. It could be A, C, D, B, E, or whatever you have. But at least we now know we've got an ordering where A must come before C, which must come before that final set of 3. Any questions on how I ran that algorithm there? Yes? So as you are, right, and I'll show you some code at the end, you are probably going to have to keep track of those in-degrees yourself in a separate structure. You will find, like I said, like pretty much you don't really implement graphs as actual like node objects with fields inside of them. Instead, you have just sort of this delightful collection of maps that's like vertex label to in-degree. Then you can look it up with a hash map. That's usually what it is. You can update it. Okay, great. Since everyone's so comfortable, go ahead and try it yourself. So go ahead, Let's take 2 minutes, work with the people around you, and produce for me a topological sort of the following graph. Go ahead. Oh, I guess I should update this now. This is out of date. Yes. Okay, let's see how we did. So, like I said, there can be multiple correct orderings, but does anybody want to raise their hand and tell me what's the first course in their topological sort? What's the first course they would take? Yes? Math 126, a freshman classic, truly. Okay, let's see if my animations, oh, okay. Oh, I put it all together. Okay, Math 126, what is the other correct possible start value? Way in the back. CSE 142, absolutely. That was my first ever coding class, fall quarter, freshman year. Not that long ago, obviously, because I'm so youthful. Okay, after Math 126 and CSE 142, what comes next? What's the next class? What has to be the third course in our DAG here? Yes. 143, exactly. So you could have either had 126 or 142 first, but 143 has to be the third because it has two prerequisites. It doesn't matter if you took, math or CSE in the same quarter or in different quarters, but you had to take both of them before you got to CSE 143. Okay? What do we have after 143? What's one of the possibilities that comes after 143? All right, our friend in the back. Yes, please. Of course it's 373. I know you took that before 374. Just kidding. I also teach that class. I love them both, mostly equally. Yes, so 373. The other option is 374. And then I will reveal the final one is 417. Any questions on how this algorithm is applied? I also hope this is a bit more clear of an analogy as to the use case for this topological sort. Like I said, it is literally how your computer determines the order in which to compile your code files. But you can think of it as the ordering by prerequisite. Yes?
So why does Math 126 come before CSE 142?
I picked it. It could be Math 126. It could be CSE 142. If I were to ask you to do this on some type of exam or something to give us a deterministic order, I'd probably say in alphabetical order or something. But yeah.
If we were doing this on a computer and compiling and there were multiple steps that didn't have dependencies, would we just use a random seed, or is there a hierarchy that uses to choose when it's arbitrary?
Oh, in the actual compilation? It totally depends on the compiler and the language, but I can tell you that there are some compilers that are really smart and they intentionally do the ones that are going to have the least amount of runtime or where they can parallel process or there's a bunch of sort of logic within the computer to decide how it's going to process those. Yeah. We can get deep into it. Take compilers. It's a really cool class. You could talk about it for 10 weeks if you want. Yeah, in the back.
Why did you add a direction from 417 to CS 142? So you have to pick math.
So are you talking about one of these arrows down here?
I'm sorry, I have to say. So why did you add a direction from CS 417 to CS 142?
Oh, like what if there existed another arrow that pointed from 417 back to 142? Then we would not have a directed acyclic graph. We would have a cycle in the graph, and thus you could not run topological sort. So if a cycle exists, you cannot run this algorithm. Does that answer your question? Yes. Well, so for example, if that happened, then what I would do is I would come back around and I'd see there's another arrow, and it would try to put 142 at the end, but it realizes 142 has to be at the beginning, and you would get in this like crazy cycle. And like that's like we need an ordered sorting of it. So like it just doesn't make logical sense to apply this algorithm to a cycle like that. Yeah. Cool. Okay. Great. Yes. Oh, look at this. Look at Past Casey put a whole slide about answering that question. Great. Thanks, Past Casey. There you go. Okay. I swear I look at my slides, but ADHD, man. Okay. Here is some pseudocode for you if you're interested in it. You can see there that we sort of do get this sort of like in degree equals 0. We add it to the perimeter, we add it to the visited, and then we go in and we update the in degree every time we like process something. So this is just the code version of what I sort of talked through about determining the in degree, erasing the like counts from that node as we process it, and then just cycling from in degrees of 0 to the very end. Cool. Oh my gosh, we have just enough time. Amazing. Okay. So we are going to spend all of Friday on the next topic, but it is such a big topic that I actually need the wonderful TAs in section to run through this algorithm with you the first time. So I'm going to just give you some language. Please go to section tomorrow so that you can practice running this algorithm. It's just the kind of thing that's easier to run on a piece of paper than having Casey shout at you about it. Also, this algorithm I'm about to talk about is the one you will implement in P4. Okay, great. Justification. We're all on board. Okay, so the shortest path problem. So what if I asked you not just to find if there exists a path from S to T, but specifically the shortest way to get there, which is pretty much what you're always asking Google Maps, right? Anytime you put in 2 destinations on Google Maps and you ask for the directions between them, literally Google Maps is implemented with the graph. What it's doing underneath the hood is running the shortest path algorithm. So we know that BFS will give us a way to find if a path exists. What if I could just take this code and add in a little bit of extra calculation so that as I go along, I just count how many jumps it takes until I get there? That's all that's happening here, is I have this sort of distance 2, and I have this map from vertex to distance 2. And so what's happening here is that when I run BFS, I finish with this full map that has all of the vertices as keys, and then the number of jumps from the source vertex as the value. So I sort of process the distance from the source to all the other vertices just by counting how many jumps it takes me to get there. Great. So you could imagine, there we go. We're just sort of keeping track as we go along. Great. So this is, you can imagine, the sort of map of the counts of how we traveled through this. Great. Now, we talked about ST connectivity. That was just like, does a path exist? We just talked about like how we would do this if we had unweighted, undirected, rough edges, and that distance was just based on like how many jumps, meaning like 4 vertices away, 2 vertices away. But you can guess where we're going with this. What if we actually had weights? What if we had distances to travel? What if we had traffic in the way? What if we had incline? We don't want to bike up. And we want to specifically not just find the singular path, but to find the optimal shortest path. This is called Dijkstra's algorithm. Again, it is named for Edgar Dijkstra, a Turing Award winner, another delightful ancient man. And it is technically a piece of code that uses BFS, that adds that map like we sort of showed, but it starts to do a few extra calculations along the way so that instead of just sort of arbitrarily picking which neighbors like we do in BFS, now we're always going to pick the neighbor closest. This is called a greedy algorithm. You're going to run through it with the TAs on Thursday. Please go to section tomorrow. I promise you it'll be worth it. And come back on Friday where we're going to dive real deep into this stuff and some other fun algorithms. Thanks so much, everyone. See you Friday.